Now let's talk about the applications of Gauss's law. Applications of Gauss's law include finding electrical fields of uniformly charged wire of negligible radius, or large thin flat planes, or two parallel flat planes, inside outside of a solid cylinder, inside or outside the porous shell, inside and outside a solid charged sphere of density rho. So we will slowly walk you, I will slowly walk you through each of these individually. So we will talk about an infinite line of charge. We will also do an infinite sheet of charge, and then a shell of charge, and so on and so forth. So let's start with the simplest of cases. What about an E field due to a point charge? Okay? If you have a point charge, let's assume this is a positive charge, right? You will have a field this way, separated out. Now, if you are going to use Gauss's law in order to solve it, what you're going to need is to draw a Gaussian surface. The most logical Gaussian surface to draw that will be taking into account all of the flux that's coming out of this positive charge will be of this kind. So once you have that done, so this is going to be my Gaussian surface, right? What is the next step? I know that Gauss's law says E dot dA is equals to Q over epsilon naught. Q enclosed over epsilon naught. My chosen Gaussian surface allows me to take E common out of the surface because E is uniform and constant over this Gaussian surface area, which will be Q over epsilon naught. Now in this case, dA will be equals to this surface, it will be 4 pi r squared Q over epsilon naught. So E will be Q over epsilon naught, 4 pi. And if I want to make it, okay, let me write it the way it would be. Q over 4 pi r squared epsilon naught. Or I could rearrange it as 1 over 4 pi epsilon naught Q over r squared. Now next, let's talk about the E field due to a spherical shell. Now what about a spherical shell? Okay, how will the E field behave? So you have a shell that's spherical, so think about it in 3 dimensions. What would it be? So my Gauss's law says E dot dA equals Q enclosed over epsilon naught. So my surface for this charge, if let's say this is R, is the radius of my shell, then my Gaussian surface has to be outside it, right? So my Gaussian surface, I'm going to assume that my Gaussian surface is a shell, which is outside this surface, right? And I'm going to call that the radius of this Gaussian surface, imaginary surface, is equals to little r. So then what happens? If I was to look at this surface and I was to make this surface on the inside, let's start about that first. So on the inside, is there any E field? So for r less than r, is there an E field? And the answer is no. On the inside, there will not be any field. So this is going to be my picture here. Okay, so if my E field is here, this is 0, this is big R, and that's R going forward. Okay. On the inside of this shell, what is the E field? Absolutely 0. There is no E field on the inside. But what about when R becomes greater than R? In that case, it will be E dot dA will be Q enclosed over epsilon naught. For this spherical surface, it is going to be E dA Q enclosed over epsilon naught, which is going to be 4 pi r squared Q enclosed over epsilon naught, and that's going to be 1 over 4 pi epsilon naught Q over r squared. Whoa, that's pretty simple. And it looks very similar to the one we just did. Now, what happens here? So in this case, my E is proportional to 1 over r squared, right? So on the outside, my E is proportional to 1 over r. So somehow, that's kind of what the graph is going to look like. As it goes away from the shell, as my sphere becomes bigger and bigger, it kind of falls off as 1 over r. Next, let's talk about a spherically symmetric charge distribution. So a spherically symmetric charge distribution. Okay, what will it look like? So I will have some charges distributed in a sphere, right? Now, in this case, what will happen? If this is my spherically symmetric charge distribution, I can actually draw my Gaussian surfaces. I'm going to have two Gaussian surfaces again. One is going to be when r is less than r, and one is going to be when r is greater than r. Okay? So my spherically symmetrical charge distribution, let me say that that has a radius r. I'm just going to assume that the radius is going to be r. So then in two cases, I'm going to have when my Gaussian surface is inside here. So for example, I'm going to call this, say, R1, and I'm going to call this one R2. So R1 is less than R. What do you think is going to have? Is E going to be 0? No, E is not going to be 0, and part of the reason why E is not going to be 0 is because there is still charge on the inside. Okay, so we are going to consider two cases. One is going to be when r is less than r, and the second case will be when r2, which is greater than r. Okay, so these are the two cases that we are going to talk about. Okay, so what is our first step? Because we're using a Gaussian surface, we have to write the Gauss's law. So in each of these cases, it's going to be E dot dA will be Q enclosed over epsilon naught. So this is the Gauss's law as we know it. Okay, so now let's talk about what happens in case 1, when R1 is less than R. Now, what happens in this case? Now, Q enclosed is what we are looking for, right? I only need the Q enclosed that's in this area, right? That's the only Q enclosed that I am worried about. So my Q enclosed ratioed over Q total will equal the ratio of Q enclosed to the volume to Q total is the same as the volume that Q enclosed has divided by the total volume. Okay, so this means Q enclosed is actually equals to R1 cubed over R cubed Q total. Well, that's one problem solved. Okay, then Gauss's law says E dot dA will be equals to Q enclosed over epsilon naught. This Q enclosed will now become R1 squared cubed over R cubed Q total. Okay? This E comes out common. dA will be R1 cubed over R cubed Q total divided by epsilon naught. Now this is a sphere, and sphere will have 4 pi r squared. Again, now which is this r going to be? This is going to be R1. Okay? which is equals to R1 cubed over R cubed Q total divided by epsilon naught. Okay? So I can simplify this as Q total over 4 pi epsilon naught R1 over R cubed. Okay, number 2. For this one, what is Q enclosed? Well, Q enclosed for number 2 is just Q total. So in that case, E dot dA will be Q total divided by epsilon naught. E comes out common, dA will be Q total over epsilon naught. So this implies E will be 4 pi R, big R, squared equals Q total over epsilon naught, because that's the surface that we were going to have. Oh no, I called that R2. Oops, sorry. So this should be R2 squared, right? So this means E will be Q total over 4 pi epsilon naught R2 squared. So if you look at this very, very carefully, what do you see? This is very similar to if there was a point charge here, whereas this one is slightly different because this one includes these terms. So that means that the total charge, the total E field on the inside is going to be different from the E field on the outside. So graphically, if you were to plot this, what would it look like? If you were to plot these 3 surfaces, what would they look like? Well, on the inside, you can see that E is proportional to R. As little r changes, E goes up. So it goes up until here, which is R, big R. And once that happens, E now becomes proportional to 1 over R squared, right? So then it decays off, just like the case it was before. So in this case, E will be proportional to R, and in this case, E will be proportional to 1 over R squared.